Okay, so we are going to talk about state functions, and state functions that you know is what are the example of state functions that you guys know? Anyone? Yes?
Enthalpy.
Enthalpy. What else?
Gibbs free energy.
Free energy. Whatever you guys know have a name in it. All state functions. What else? What about this? Internal energy? Is there anything else? What about entropy? That's the one is going to the next chapter, chapter 3 stuff, and that's the one that actually will be also introduced. And also, I mean, it's obvious, but temperature is state function. Yeah, once you define the state, it was defined by the state. Temperature, volume, these are all state functions. I guess the more important question is which is not state function. This is something that you have to deal with. There are two main things that thermodynamics deal with. First one is Q, the other one is the work. Okay? Heat and work is not state function, and that's the one that it's going to be. So when it's a state function, I can easily say change from one state to the other. Right? Change in one state to the other. So these are the symbols that people all using it. Whereas this one, if you write this way, I mean it's okay, but it's not a good idea to write this way. So people write Q, which is itself is a change, right? Or is a process defined by the process. Whereas this is defined by the state. Whereas this is defined by process. And we are going to deal with different process. The one that's going to be very useful is there are two processes that's going to be useful, which is delta T is 0 or Q is 0. These are the ones. Two processes that we are going to deal with in this chapter throughout. How do you call this state, this process? You call it constant temperature, right? Isothermal process, right? What about Q equals 0? Does anyone remember? Adiabatic. Thermal insulated wall. So if you have like what she's drinking, the thermal wall is not permitting any heat flow, so there's no heat goes in and out. So it's an isolated system, so adiabatic system that we are going to talk about. And this is going to be quite a lot involved in here. But anyway, let me talk about exact differential. Let's start with this. So at least for today's class, I want to make a big deal about this. Is when we say change in the internal energy, because that's the main portion of the chapter 2, it is a change in the U from initial state to final state. This is kind of philosophical argument. This is a initial state, final state. If you know your U changes, there will be delta U. So U is internal energy. That's a state function. Once again. And we love to write this way. I'm going to put this big thing. This is what I want you to remember. That's a notation for exact differential. Okay? So when you have a small change, differential small change in the state function, we use this symbol D from. And I want you to compare that here. We are using this. Okay? And I hope you are not using this symbol. It's not really a good idea to using this symbol because this is really, this D is for the something that deserves to write the D is for the state function, but this is a non-state function, what we call the path function or process function. So they are using this wiggly, or just do this. Unfortunately, textbook also using this. Just remember that this D is not the same as this D. Okay? This is, I don't know what Dr. Atkins decided to do, why he put it this. This D is not really represented in the correct way because this quantity is not exactly differential. And when he wrote the like earlier version of textbook, he has a clear distinction that this is for sort of the differential, but not mathematically well defined. Whereas anything that mathematically well defined, they use this D or that. Okay. So the most important practice with you is so now this one is I want everyone to bring a piece of paper and write this one with me. This is a very important practice that you do to deal with the multi-dependent variable, and then let's do this. So if you do not write, don't worry. This is all scanned and you can download LMS. But it's still a good idea to just write down as much as you can in this class. So let's think about this. Okay, so I want to understand the internal energy. This is an internal energy that we have, and like I said, I'd like to bring this piece of syringes. And we have this gas molecule, right? Defined by whose energy, internal energy in this gas molecule, in this piston, by its own temperature, right? Temperature is the most important one. Another thing that is also can define on the internal energy of the gas in this one is volume, or pressure. You can choose. So like I said, we have a peak 2 business, and then my first choice is definitely temperature. That's a kinetic and dependent. And then here, their peak 2 choice is the volume. Okay? So, and then what's an important practice one is, this is peak 2. And my choice is temperature and the volume. Okay? And see how this changing the volume, or changing the internal energy, what I'm going to write is the same as you change your volume or you change the temperature. This one should make sense to you. That's the first thing. When you want to change something, right? When you change this one is depending on the change in the two independent variable that affects the defined state of the internal energy. So I can write this. First step, right? And then what goes in here is a partial differential. So the next step is, okay, this is a partial differential. And because of you are changing the V volume, so you are having volume change. This one is a temperature change for to cancel out each other. And what goes up is your internal energy. So internal energy depends on the volume change. Internal energy depends on the temperature change, and that's a partial differential. So this is pretty much what you ended up writing. And I think it's a good practice for you to have this one break it into two differential terms, and then how everything worked out. And finally, because of the dependence on this, and this is a partial differential, when you change the volume, you keep the other constant. What's the other? This one. Okay? So when you change the volume, you keep the other variable constant. So this is essentially you want to say temperature to be the constant. So this one, when you change the temperature, you keep the other one, which is the volume. So that's the one. So that's it, right? So I think that I don't mind you guys say somebody, oh yeah, I think I have seen this one before, and I'm writing the same thing again. Okay. I just wanted to nag you that why don't you write this first and trying to write this one next. This is a good practice for you to kind of understand. This is just a very kind of generic description. When you want to see the change in the internal energy, that can be described by volume change and temperature change, and the one goes in front has to be just simply mathematically defined this way. That's all I'm saying. The only statement that I had is actually I did a pick two, and my choice is volume change or temperature change to describe the internal energy change, and this is something going in front. So now we have to deal with this new two quantities shown up here, right? So this is the number 1, 2. And so let's think about internal energy divided by volume change when you keep the temperature constant. And this one we call pi p, and it has a name of internal pressure. Okay, so it has a definition of what is for internal pressure. So now this one is pi p. I just put a new symbol on the term that is shown up here. Yeah, so what's the unit on round U? So let's think about it. This is a pi. So let's just think about the unit. What's the unit of internal energy?
Joules.
Yeah, joules, which is an energy. I like joule. I don't mind. Put a joule there. What about the volume change?
Meters cubed.
Volume. So which is what?
Meters cubed.
Meter cube as an example. So what's the unit for energy divided by volume? That's right. You remember that? Pressure times volume is an energy, right? So energy divided by volume is an energy. The energy divided by volume is a pressure. That's why it has a name called pressure, internal pressure. So it's just a name that happened to be, this one must have a unit of pressure. It has a unit of Pascal as an example. So that's it. But now think about the meaning of, do you remember in the first class I talked about this any thermodynamic variable that we want to understand more, sort of put it in this way. When you change something, this is a response from the system. Remember that? So what do? You change, this is what you do. You change your volume. So when I change the volume, what am I doing? So you are here and you change your volume. What's going to happen to the molecule? You are? By doing it, what am I doing to the molecule here? Yes. You're bringing molecule together, closer together. So you're controlling the intermolecular distance, right? So I'm interested in this, and then my response is, think about it, internal energy change, right? So that's your response. That's what this one is about, right? Keeping T constant. So this is a whole kind of the statement about simply write this way. I want to know how much of the internal energy change when I change intermolecular distance by changing the volume and keeping the temperature to be the same, kinetic energy the same. All right? So this whole statement is nicely written in this way. And then, okay, so if I compress the gas and changing the volume, bring the gas molecule closer together. And if they have no interaction, just like an ideal gas, what's going to have an internal energy? If there's no interaction, it doesn't matter how closer you are, how far you are, the energy level is the same. Right? If it is an ideal gas, this distance change has nothing to do with the internal energy. Okay? So therefore, conceptually I already know high T, internal pressure, and the constant temperature is 0 for ideal gas. That's one I've already found out. So if you do this, the one that once again is here now, this is a pi T volume change. What about this portion? Internal energy change, which is like a heat under constant volume. And you change the temperature, delta T. You know what this is? This portion is CV, right? Heat capacity of the constant volume. Temperature needed to change certain temperature, and that's how heat capacity is being defined. So the one that I wrote is CVdT, and so that's the generic equation for that. And like I said, ideal gas, all of this will be a du CVdT because pi T is 0. So that makes your life easy, and your internal energy solely depending on one variable, which is temperature. Well, what about the real gas? And here I want to use an example as van der Waals gas. And actually your pi T is I think the A times NV squared. So this is not 0. Okay? Okay, once again, remember, this one is, I want to know how internal change, when you change the molecular distance, keeping the temperature constant, and that's the internal pressure. And you guys remember, when A is positive, what kind of an interaction do I have? For van der Waals gas, you just took the quiz yesterday, or last class. What kind of attractive